This is the last section on dynamic logic, and it's basically the true single phase clock logic, and most likely used for registers. So it's a similar idea that we saw before, where you had like an N-type section for pre-charge and evaluate, followed by a P-type block with pre-charge and evaluate as well. And then at the tail end of both of these logic blocks are these N-half latches, which are, as you can see, everything controlled by phi with no clock inversion. So the N block has a pre-charge and evaluate, and the P block has a pre-charge and evaluate. So there's that same picture again, sort of shown in the master-slave mode, with the N-type section preceding the P-type section with the pre-charge on phi equals 0, and then the N-type section evaluates on phi equal 1, and the opposite for the P-type block. Here's an example with some logic embedded into it. You'd have to sort of go through a timing diagram and see how it functions properly. But in this particular case, the main point here is it's one clock. So there's no phi bar on this figure at all. And you could certainly simulate that with any type of a switch level simulator. Here's an example of an edge triggered latch, which is what you'd more likely see. And this is a negative edge triggered behavior, and basically it's our N-type block followed by our P-type block and just an inversion at the end. And here's a couple more examples of the positive edge triggered D flip-flop or negative edge triggered, and the positive edge triggered D flip-flop with split output latches. So that's that part at the end here. So the in-class assignment here is to build a true single-phase clock NOR gate and verify its functionality. So basically you just insert some logic into the true single-phase clock latch. Just a little summary now. We looked at some basic CMOS logic gates, and the primary one we looked at was a fully restored full static CMOS. And there's a number of factors that continue to drive CMOS. One of them is the advanced processing for CMOS, the increased capacity of modern die, and certainly one of the big drivers also is the high-level synthesis and system design, where a lot less emphasis really goes into the circuit design and much more emphasis goes onto the system design. So there's a lot less regard for actual transistor count. We looked a little bit at dynamic CMOS as which may be a possible alternative to static logic. In certain cases, it's going to have faster operation with smaller gates and hopefully lower power dissipation. Certainly when it's dynamic, that implies that it requires a clocking strategy in addition to things that you have to worry about like race and hazard avoidance. We looked a little bit at this cascode voltage switch logic and the dynamic version of it, which may be an attractive alternative to static CMOS. And certainly we'll sort of see them when we look at some memory structures, and we'll see that it kind of looks like that in any event. We looked a little bit at NORA, which was sort of the cascade of the N-type dynamic logic followed by a P-type dynamic logic. So allowed it to be cascaded quite easily, and it basically compared it to like domino and other types of structures that we looked at. And then just briefly looked at the true single-phase clock logic, which is really the state of the art. Probably if you have any type of dynamic registers, they're going to be of this nature here. And this is a very nice structure, because you can build edge-triggered behavior attained by cascading two of those blocks with the C-squared MOS output. And the main point was no clock inversion and or non-overlapping clocks required. So it's a bit like evolution. We sort of saw some fairly complicated dynamic structures, and then at the end we came down to the one that just had a single-phase clock. So here's sort of a summary of a bunch of logic families. The ones that are in green are probably the must-know. You certainly have to know the static CMOS in a fair bit of detail. Probably at least be aware of the true single-phase clock logic, and the others to various degrees, and a whole bunch that you really don't have to know too much about in any event. But, from a circuit perspective, they have some interesting characteristics. So why this stuff might be useful? Well, sometimes it's a good idea to see what's been done in the past, for example, and perhaps improve upon it. It may be used again in the future. Dynamic logic, for example, might be a good choice for parts of the circuit where extra engineering investment is justified, and certainly that would be required, and that might be along critical timing paths and pipelines. This is an in-class assignment that we'll do together, basically building up an FPGA architecture and incorporate some of the circuit techniques that we saw a little bit previously. This is a circuit design trends taken from April 2008. It sort of just highlights from a circuit's perspective what's happening in the area, although it's a little bit dated. it sort of points out that there were some technology alternatives in the 80s and 90s. BiCMOS, for example, was one of them, and a lot of the work in digital circuits was driven by processor design, and these new systems is where the problems were most acute. So primarily it was going to be power dissipation and being able to manufacture the chips in the first place. So by the mid-1990s, it was pretty clear that plain voltage scaled CMOS was going to win, and it certainly has continued to do so to this point in time. Clock distribution and latch design became a big challenge during the 90s, and if you look through any of the papers or references for the latches and flip-flops, you'll see a lot of that was done back then. And the principal issues sort of in the early 2000s were reducing power consumption, because for a CPU, power dissipation grew to around 100 watts, which was right at the limit of many cooling solutions that existed. So some of the early technology drivers were the high-speed links and the low-power circuits, and these initial approaches, as you might imagine, were trying to minimize the CV squared type of power dissipation that associated with switching circuits. So you want to be able to reduce the voltage, you want to be able to scale the devices to reduce the capacitance. So scaling voltage and technology means a scaled threshold voltage, and that comes at a cost of increased leakage, and this would be fairly notable in portable applications, which was also one of the technology drivers. Here's an example. Pentium 4 used low threshold gates for critical paths and normal threshold gates elsewhere for reduced leakage. And what we saw earlier with some of the FPGA technology, they adjusted transistor thresholds dynamically by varying the body voltage. So you're choosing a threshold voltage just low enough to run at the speed selected. So their summary was that the job of the digital circuit designer has grown with the chips, moving from optimizing and validating the gates themselves to working on functional units to now complete systems. And remember that that little overview is sort of a circuit perspective, and probably a little less emphasis on system design than you might otherwise think. And that brings us to the end of that section.